I was saying optical metrology, why do you need it? The idea is to show you that the system are so complex that you actually do some kind of navigation system for front-end of line processes. So why do you need metrology? Well, ideally, all processes should be uniform. So wafer to wafer, the wafer chip to chip level, run to run level, and in space from system to system and fab to fab. But actually, neither the world nor our processes are uniform. And so the metrology helps you narrowing variances and navigating toward consistent processes and devices. And this is basically what LayTec can do for you. LayTec is an optical metrology company, and we are producing optical metrology for in-situ monitoring. And we are based in Berlin since 25 years, a spin-off of the Technical University. And there are some data about our history and our part of this dynamic group. The business, as I said, is process integrated optical metrology. The particularity is that most of our sensors actually work during epitaxy or etching, and also in between as a mapping station in between. Markets are semiconductor and lithium industry and academia, and they include lighting, laser, photovoltaic, and glass coating. Now, a look at production manufacturing chain of semiconductor, we see that there are several steps, and in these steps you are in for cost, you can produce value, and you also have some risk or opportunities. For example, if you look at starting from the substrate to the epitaxy, that's the first step, you get lengthy processes and high costs because you go from wafers to wafers with the device, planar device on top of it. And here you have high value generation, and you got to keeping under control both temperature, thickness, and the composition of the materials. One thing that you don't know after you finish the epitaxy is how uniform it is, the distribution of these characteristics on the wafer, and then also after that you go to go some other steps like etching, for example. You can again maintain this or destroy the activity if you have a wrong etch step point. So for this reason, to control all of these steps, we proposed and we implement our in-situ metrology in ex-situ mapping, in-situ metrology, which is at the level of the front-end epitaxy, the ex-situ mapping between different epitaxy steps, and also again in-situ metrology during etching. And this is what we propose as a concept of connected metrology. So gather information throughout the front end line of the process in order to understand better what's happening to your needs. And let me discuss this in particular with an example of GaN-on-Si end production, where we show how it is possible to control to very high accuracy film thickness during MOCVD and etching. So basically, there are two main type here of devices. One is this D-mode HEMT, which is the one that I show here, where you have to start with a GaN buffer to do strain engineering directly grown onto the silicon. Then you grow an intrinsic GaN channel layer, and then an argon barrier. And this would be now the D-mode HEMT, high electron mobility transistor. If you add another step on top of it with the P-GaN gate, then you get an E-mode HEMT device. This difference between E-mode and D-mode is this is enhanced mode, the other one is depletion mode. And I'm not going into the details here, but actually you want most of the technology now is going toward the E-mode because it allows you to produce transistors that are normally off. For cost reason, these are grown on big silicon wafer, 200, 300 millimeters diameter, and then extreme uniform AP and etching are required. So the optical in-situ control at that level of half a nanometer, basically one atomic monolayer, is a must. Let's take a look at the MOCVD. You see the animation on the right side of the screen. Our tool is typically is the one that you see at the bottom left side of the page is what we call LayTec epigraph TT. We are measuring, and this is inserted. This is embedded in a reactor, in a MOCVD reactor. This is typically measuring every about 2 seconds temperature with multi-wavelength reflectance and local curvature on the way of the wafer. At the center of a specific wafer or a radial, and also we can also do a radial scanner cluster wafer. This would be the center of the specific wafer. As you can see here, the wafers are rotating typically under a viewport when we measure to the viewport. The in-situ measurement is highly sensitive to, and this sensitivity is a constant from the first layer to the last layer over typical growth times of hours. So layer-specific deviation can be detected then in real time and in the process, and then used to do advanced process control. But there are some drawbacks like limited accuracy for very thin intermediate layers, and the fact that you cannot read it to the scans. So what we can use to overcome this is doing post-AP wafer mapping, like with another of our tools, which is the APEX system mapper. It has several characteristics, as you can read here, and then in the slides that you will be receiving afterwards. But the main thing that I want to concentrate now is the accurate measurement and fit of UV reflectance of these product layers. Why this is important? Because if you're looking either at D-mode and then also D-mode devices, you want to determine very accurately the argon barrier composition and thickness, and this is usually done now ex situ with the photoluminescence, which is not as accurate as our reflectance measurement, because the reflectance measurement, is measuring the argon barrier, the whole of the argon barrier. And so that's, if we do UV reflectance fit, we can get both the composition and the thickness. And the similar results we can also get on the EGAN devices, on the E-mode devices. Here there is the problem that the EGAN on top is absorbing some light, and so it's reducing the capability, the measurement capability of the photoluminescence, for example. That's why it cannot be used in this case. But since we know from the AP how the wafer is structured, then we can join together this measurement before and after the AP, and then get to a very high accuracy in this in determination of thickness and composition of this crucial layer. And last but not least, the etching and the endpoint, as I was mentioning earlier. Standard way would be to do optical emission spectroscopy, but this requires edge stop layers, which is only sensitive to the interfaces. Again, we are using an advanced approach with the UV reflectance, and then an example is shown here in the right. This is now the reflectogram that you would measure during the growth of this HEMT device. So you see that there is the oscillation at around 5 nanometers because of the material that's absorbing the light, and then you get for the argon barrier, which has a different extinction coefficient, and then again you can single out very accurately the pGaN material here. If you would think of time reversing this kind of interferogram, you would look first at the pGaN layer, then the argon barrier, and then the buffer. And this is actually what's happening when you are etching the material. And this here is an example of in-situ measurement done during the etching of the etch through of an HEMT structure. So at the beginning, we see very clearly the pGaN and argon layer, and then we are also measuring the 3 different wavelengths at the same time, and then we can get information throughout the etching the etching process, and basically we can decide in where to stop with a very exact, with a very high accuracy throughout the wafers, throughout the structure, not only when there is an interface there. And so, as a summary, I would say that, let's say, what we can do for you. Well, we can help you with narrowing variances and navigating toward consistent processes and devices in the round-to-round system to system, in fact, to fab uniformity with our connected metrology. And what you can do for us is tell us about your challenges and let us work together to overcome them. Now I'll finish with the kind of sales pitch saying that, yeah, then choose LayTec metrology as your navigation system, and I'll thank you for your attention. And I'm ready to answer your questions.